First thing to do today, though, is to think about Taylor polynomials as approximations to functions. We know this equation, e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. As long as that's an infinite series, you get equality no matter what x is. And x could be humongous. It could be Google to the Google power, which is a Googleplex. It could be another Googleplex factorials after that. It doesn't matter how big x is. This is equal. This converges for all x, and it's equal to that for all x. But we never actually proved that it equals e to the x for all x. We never really proved that. You're just trusting me. Today, I actually want to prove that using a theorem called the Lagrange Error Bound theorem. We'll use the theorem to prove this is equality, but we won't prove the Lagrange Error Bound theorem itself, though the proof is in the book. The question we want to answer to lead us toward that is, how good of an approximation do we get if we truncate the series, stop it at some point? Is this one. How good of an approximation is e to the x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. But stop it somewhere. Make your highest degree be nth degree, x to the n over n factorial, and then don't do any more terms. So that's a finite sum. Which, by the way, with summation notation, and you should continue trying to get practice with that. One way to write that would be the summation k goes from 0 to n of x to the k divided by k factorial. This summation here has n plus 1 terms, but we call it p sub n of x because it's an nth degree Taylor polynomial approximation. The series up here, where it goes on forever, we've been calling p sub infinity of x, as if it were an infinite degree polynomial. Again, as if we were adding infinitely many things, even though we are not literally doing so. How good of an approximation is this? That's our question. To answer that, we need the Lagrange error bound. But before we can write down the Lagrange error bound, we need to understand error. The error in using p sub n of x to approximate, in this example, e to the x, but in general to approximate f of x. Let's call this f of x here. The notation in our textbook for this is capital E sub n of x. And just like with numerical integration, when we were approximating integrals numerically, for example, with Simpson's rule, the error was the actual value minus the approximate value, alphabetical order. That same thing happens here. It's the actual value of the function minus the approximate value that you obtain from the Taylor polynomial. The actual value is f of x. The approximate value is p sub n of x. So this is the definition of the error. By the way, another way to write that is often used is to solve this equation for f of x by adding Pn of x to both sides. You can write the function as the Taylor polynomial approximation plus the error. And that's part of the reason why error is actual value minus approximate value, is so that you can have a plus sign there when you solve for the actual value. It's kind of nice. But I'll remind you, if the approximation is too big, Pnx is bigger than f of x, then that's actually a negative error. If it's too small, it's actually a positive error. It's a little counterintuitive. What does the error bound theorem say, or what is the Lagrange error bound? Under quote unquote nice conditions. How nice? Your function f is nice. It's continuous. Its derivatives up to a certain point exist. In fact, if we're after the error in the nth degree polynomial approximation, we want the derivatives through the n plus first derivative to exist and be continuous, it turns out. The absolute error, which is the absolute value of the error, which does equal the absolute value of this difference, I'll remind you, is less than or equal to something. It's going to give an upper bound on this error that we can use, for example, to figure out how good an approximation is over a certain interval. Probably more importantly, though, what we hope to have over here is a quantity that goes to 0 as n goes to infinity. For a fixed value of x, we would hope we get something over here that goes to 0 as n goes to infinity, which makes the error go to 0, which means f of x or Pn of x approaches f of x as n goes to infinity. That's what we're hoping. The form of what goes over here is traditionally denoted by a capital letter M divided by n plus 1 quantity factorial times the absolute value of x minus a to the n plus 1 power, where a is the location, the value of x that you are expanding the Taylor series about. And 90% of the time or more, a is 0. Did we even do one example here where a was not 0? Not in class maybe, but in your homework you did, at least one. Well, okay, that's fine. Well, but what is m? Where I could describe it in words this way, but then I'll write it a little differently. M is an upper bound for the absolute value of the n plus first derivative of f over the entire interval between a and x. Yeah, that's a mouthful. I'll write it. The absolute value of the n plus first derivative, right? If you put the numbers inside parentheses, it means derivative. So we don't have to just write a bunch of primes with dot, dot, dots. N plus first derivative of f, evaluated where? I'm going to use the letter t here. And this is less than or equal to capital M in absolute value. For all t between the number x and the number a. So if, x is bigger than a, then t is somewhere in there. T in here. If x is smaller than a, which it could be, then t is somewhere in here. I want to think of the a and the x as fixed when I think about using this inequality. I'm interested in what happens as n increases. Usually we would imagine x to be bigger than a, but it could be less than a, which is part of why you need absolute value signs there. Is this a quantity that goes to 0 as n goes to infinity? It kind of looks like maybe that's the case. I mean, n plus 1 factorial gets large very rapidly and you're dividing by it. On the other hand, if x is further away from a than 1 unit, like 2 or 3 or 4 or 5 units away, then this quantity raised to the n plus 1 power also gets big as n gets big. So which one wins out? We will see with some numerical evidence in Mathematica that the factorial wins out. If m is a constant, at least, this goes to 0 as n goes to infinity. Now, there's still a trick, though. How do you know m is a constant? Could it depend on n? Actually, in some cases, it does. So this is not always useful for proving the error goes to 0. But in the most important cases, it is, okay? Like e to the x, for example. So what would this mean in the context of thinking about f of x equals e to the x? So f of x equals e to the x. We're using a equal to 0, because that's what we do 90% of the time or more. Pn of x, I already wrote it down. I'll write it down again, both in the summation notation and write it out. We're using this truncated Taylor series, this Taylor polynomial, to approximate f of x near a equals 0. We hope it's a good approximation when x is close to 0. What would the error bound theorem say in this case? Well, not much more than what I already wrote, except we can figure out m. We need an interval, though. What interval should we do? We could pick a particular one. The word over there. We could pick a particular one, like say, well, with an arbitrary endpoint, but centered on 0, say negative b to b, maybe. Over the interval from negative b to b. What's the value of m if that's my interval? That's the question. So x is somewhere between negative b and b. A is 0. M, again, is an upper bound for the n plus first derivative of the function. Well, fortunately, with this example, all the derivatives are the same as the function, right? The derivative of e to the x is e to the x. Second derivative is e to the x. Third derivative is e to the x. All the derivatives are equal to e to the x. I could write fn plus 1 of t is e to the t. No matter what n is, for all n, for any n. And if I think about that over this interval from negative b to b, the graph of e to the t, say, if this is a t-axis, looks like that. And over this interval, it never gets higher than the second coordinate of that point right there. And what is the second coordinate of that point? It's e to the b. So in other words, I can take m to be e to the b. B is fixed. Okay, I just pick a b. We'll do an example of b in a minute here. Based on that value of b, I can replace the m with e to the b. I am using a equal to 0, so I can also replace the a with 0 and get this. Okay, let's pick a value of b now. Say b equals 0.1. So we are close to 0. The interval from negative b to b is negative 0.1 to positive 0.1. Then the absolute value of the error is less than or equal to e to the 0.1 divided by n plus 1 factorial times the absolute value of x to the n plus 1. Also, what else can I do with this? I can simplify it further, because since I'm focused on this interval, a is 0, which is in the interval. I picked the b to be fixed. X is between, it's in the interval too. So I can replace this quantity with where it's biggest, when x is 0.1. Or in fact, even negative 0.1, because you're taking absolute value sense. So I get this. I can replace x with 0.1. Part of the point of doing all this is to avoid technology, and we can avoid technology for the purposes of a proof. But to actually use this for a numerical example, I need to know what e to the 0.1 is. And so I need technology. I mean, you could guess it's just a little bit bigger than 1, because e to the 0 is 1. Maybe 1.1, maybe 1.2. You have to know you're right without your technology, though. E to the positive 0.1 is in fact about 1.1. And if in fact I want to make sure I get a definite upper bound, I should round that up to 1.11. So this becomes less than or equal to 1.11 divided by n plus 1 factorial times 0.1 to the n plus 1. And this is going to be true no matter what n is. Let's now say n is 3. So the absolute value of the error in using the third degree Taylor polynomial approximation to e to the x, according to this, is less than or equal to 1.11 divided by 4 factorial times 0.1 to the 4th power. 4 because if n is 3, n plus 1 is 4. Is that a small number? Certainly 0.1 to the 4th power is small. Yeah, I mean, when you raise a number between -1 and 1 to a large power, you get a small number. Dividing by 24, 4 factorial makes it even smaller. Multiply by 1.11. This is a 4.625 times 10 to the -6. Which if you convert to ordinary notation is 0.000004625. This is an ironclad guarantee over the interval between -0.1 and +0.1. If I use the third degree Taylor polynomial approximation of f of x, which is this thing through the third degree, to approximate e to the x over this interval, the error is guaranteed to always be less than that, no matter what x is. Let's use Mathematica to check this. So I will enter the function f of x equals e to the x, use a capital E. I'm going to enter a general nth degree polynomial into here by letting it depend on n as well. I'm going to use the palette, click this button here to make a subscript. I'm going to go p sub n underscore, because n can change, of x underscore equals, use the summation button, summation k goes from 0 to n of x to the k power over k factorial. And for example, we can see what P3 is like this. There's the third degree Taylor polynomial approximation to f of x. As an illustration of this fact, that the error is less than or equal to that, I can plug in a number like 0.1, actual value minus approximate value. This is going to be the value of the error when x is 0.1. Yes, 4.25 times 10 to the -6, which is smaller than 4.625 times 10 to the -6. You plug in a number closer to 0, the error is even closer to 0. Another way this can be verified is to, well, define an error function. I'll call it error, not error box. Error sub n of x to be the actual value minus the approximate value. Get rid of the underscores once you've defined the function. And I could confirm, for example, that error sub 3 of 0.1 is what we got before. And I could plot these things. I could plot the error function. Let's plot f of x, p sub 3 of x, and error sub 3 of x. And to make the colors clear, let's make f of x be red, P3 be blue, and the error be green. So the red graph is e to the x. Take a look at it. You can see it's increasing in concave up everywhere, and it has the x-axis as a horizontal asymptote as x goes to minus infinity. The blue graph is P3 of x. Function values match there at 0. They're both 1. Derivatives match there at 0. They're both 1. In fact, the second derivatives match there and are both 1. And the third derivatives are there, match there and are both 1 for this example. Because e to the 0 is 1. All the derivatives of e to the x are e to the x. Plug in 0. Always get 1. The green graph is the error. You can see it's really close to 0. As it should be. The error goes to 0. As x goes to 0. For convergence of the Taylor series, the important thing, though, is that the error goes to 0 as n goes to infinity. But you still do get better approximations the closer you go. Okay, now we're real close to 0 here. I'm going from negative 0.1 to positive 0.1. The blue and red graphs are so close together, you only see the blue graph. The red graph is really behind it. It was plotted first. The blue graph is the error function. You can see just pointing the cursor on there, really close to 0. When x is negative 0.0012, look at that cursor down there. The error function is close to 8.43 times 10 to the negative 14. Very, very, very close to 0. Yes, we want that to happen. It should be the case. What if I just plotted the error function by itself? Would it change the scale? I do believe so. I think it'll change the scale so that we can actually see some negative powers of 10. Yeah, 10 to the negative 6 there. Okay, so it is going to 0 very rapidly.